Hey everybody, hope that you're having a great day. Today we are going to do a quick review of area and volume. This is an important one. There is always some sort of a question that asks about area and volume on the AP test, whether it's hidden in some different kind of problem or straight up. But let's just jump in and see what we can find. So first thing, area between a curve and an axis. So if you want to find this area A right here, between A and B, the curve is bounding between the x-axis and the curve. That's just the definite integral from A to B of f of x dx. So this, back when we did this, we broke these into rectangles. Oh, if I can make a rectangle. And what we did was we made these rectangles all very, very, very skinny as possible, have an infinite number of rectangles, and that limit of the area is equal to the definite integral. It's just a way of adding up the area between a curve and an axis. Do the same thing on a y-axis too. If you had a function that looks something like this, if this was, let's call it c and d, you could integrate from c to d of, I guess you might call it f of y dy, because every y value along that little post has a height or a distance out to the function. Now, one thing to remember is that when we're doing definite integrals, negative areas, because they have a negative height, right? The height of the rectangle goes downwards. These actually have a negative effect on the overall integral. So if you integrated this from a to b, you would have a positive component here, a positive component over here, and you would have this negative component here. So just something to be aware of and to be careful of as you're doing these problems. So first thing, definite integral just adds up the area between the curve and the axis. Next up, so approximating with LRAM, RRAM, MRAM, and trapezoids, I always suggest drawing a picture. Because if you draw a picture, you'll immediately see, is it an overestimate, an underestimate, somewhere in between, what's going on. So LRAM is going to be an underestimate, it looks like, when the function is increasing, and it's an overestimate when the function is decreasing. So it doesn't have anything to do with concavity. This is concave down the whole time if we go from an underestimate to an overestimate. Anyway, RRAM, opposite. Overestimate when we are increasing, underestimate when we're decreasing. MRAM, they'll never ask you about estimates because it could be either one. With concave up, concave down, it doesn't really matter. Increasing, decreasing, just depends on like where the curve is at that moment. So they won't ever ask you about if it's an over or underestimate unless you actually have values. And then trapezoidal rule. Trapezoids are an underestimate when you are concave down. So here and here and here, it looks like we're concave down and we have open space. And it's an overestimate if we are concave up. So once again, I suggest just draw a quick sketch of these things to see what you're dealing with when you're trying to approximate the area under a curve. So area between two curves, back when we did this, we said, well, we need to make like a rectangle like that, right? And what is the height of that rectangle? Well, that distance is just the difference of the two functions. So if you want to find the area between two functions, you just integrate from a to b, top function, which in this case is f of x, minus bottom function, which in this case is g of x, dx. Now trust me, that is the formula. You don't have to think about it at all. You just do top minus bottom. And some people say, wait, but what if the function is negative, like you have with g of x right here? Well, it doesn't matter, because if you're subtracting a negative number, it's making it even taller. So like, this gives me f of x, the height of that stick. And then if I add that little bit, which would be the same as subtracting g of x, because at this point it has negative values, that'll give me what I want. So with x as a function of y, for these you're always going to do right minus left. So in this case, you would integrate, I guess we can do this, sure. From negative 2 to, I'm just going to assume that that's 4. I really hope it is. I'm not sure if it is or not, but we'll see. So I would integrate from 2 to 4. Right minus left. So it's going to be y plus 1 minus 1/2 y squared minus 3, and then dy. So dy, because as we march up here, the thickness of these lines is going to be dy. Here, the thickness of our lines is a dx. Cool. All right, so now we get into revolutions. Disks. Disks are right up against the axis that you're revolving around. Now, I was trying to find something that didn't revolve around 0. All the disk problems I found revolve around 0. But you could also do something like, let's say it was, I don't know, a function that looks like this. And they said, we're going to make the rotation line right here. And then you have this guy rotated around. Let's see if I can kind of draw a little picture here, maybe something like that. And that would also create disks. So it doesn't have to be around the 0 line. It could be around something else, but it's going to make disks. And what we have to think about here is that every single x value is going to have a different disk like this. And we think, oh, well, how high is that? What is that radius? Well, that's just equal to the function value. So if we have f of x bounding us on top here, that radius is equal to f of x. So sometimes you'll see us like draw a disk like this, and you say, well, that radius right there is f of x. So the volume is going to be the integral from a to b of pi r squared, which is pi times f of x squared dx. Usually you pull the pi out front. So usually you have pi integral a to b f of x squared dx. And that's what you're going to be looking for. So that's going to give us the areas added up of all of those disks. The dx gives us a little bit of thickness, and we add them all together, gives you the volume. Same thing, dy. You integrate from, in this case, 0 to 4, I guess. We got the numbers, we might as well use them. And then your x is going to be a function of y. So in this case, it looks like we have y equals x squared. That would be x is equal to root y. Don't really want to think about that, but we're just going to think, well, we have the pi out front, and then we'll have our f of y there. F of y dy, because dy is going to be our thickness there. So they write y equals x squared here. It'd really be more useful as x equals root y, f of y squared. So it'd be nice in this case, pretty easy, because that square root would just go away. Cool. All right, so disks, whole idea there is that you're right up against the axis that you're trying to rotate around. So washers now is really just two disks. So if this bottom function was not here, if it was just the top function, it would create a disk, right? It would create a solid disk with that big R right on there. But then what we do is we say, okay, well, let's take that smaller function, and we're going to punch a smaller disk out of it. So then we end up with that little r right there. So the little r is, in this case, g of x, and the big R in this case is f of x. And this is nice because, once again, we're rotating around the line 0. So we are rotating around an axis that we know, and the height, the big R is just the f of x value, and the little r is just the g of x value. So the volume of this guy, kind of break it into two pieces. It would be the big disk minus the small disk. So it would be pi integral from a to b. The big disk is f of x squared dx. And then we have to subtract off the volume with the little disks. So it would be pi integral a to b g of x squared dx. Usually you see this written together. Pi integral a to b f of x squared minus g of x squared. Now, one important distinction. This is not f minus g squared. You got to square them separately. If you have f minus g squared, you would have to expand it out using FOIL. It would be a mess, and it would be a different answer. So you've got to make sure you square them separately, subtract them, and then integrate from a to b and multiply by pi dx. dy, same deal. Right function minus left function. So we would have pi integral from, looks like 0 to 1, probably. Oh, sorry, we're doing dy. So it'd be 0 to 1 still. So we're going along the y-axis here. And you do right minus left. So let's call this f of y and this g of y. So every y value as we climb up the ladder here is going to generate each of those functions. So we're going to do f of y squared, always right minus left, minus g of y squared, dy. So a little trickier with the y's, but something you should be practicing, because AP loves to throw in some questions with some y's. Okay, so let's think now what would happen if we're rotating around a different axis. So if we were rotating this around the x-axis, that wouldn't be too bad. We would just use washers. But let's say we were going to rotate it around something a little bit lower. So let's say instead of rotating around the x-axis, we're going to rotate around the line. Let's say this is -1. I always think it's helpful to draw a picture. Now I'm thinking, okay, my big R is going to go from f of x all the way down to that -1. So let's think about what that distance is going to be. Well, if I just went to the axis, that length would be f of x. Now think, is my radius longer than that or shorter? Because people always mess this up. They do f of x minus 1 because they see that -1. Don't think that way, right? Just think, well, f of x gets me to the axis. That height is f of x. And then I need to go a little bit further. I need to go 1 further. And it's always going to be that 1 plus the f of x value. So if I were to draw a representation here, my big radius is going to be f of x plus 1. And my little radius, so that's going to be from g of x, and then I'm going to add 1 to that too. So the little radius right there is going to be g of x plus 1. And now we just put it into our washer formula again. So the volume here is going to be pi integral a to b f of x plus 1 squared minus g of x plus 1 squared dx. Okay, so once again, I'm using my big radius and squaring it, and then subtracting my small radius squared. Don't forget the pi, because once again, we're dealing with circles here, so pi r squared, and that's going to be your overall volume. Now, there is a general way to say this. If you're revolving around, let's say this is k. Okay, so not a distinct line, but we're just saying there's some k value that we are rotating around. This will always work. I don't love this formula because I think it's easier just to draw it out and visualize. But what you can always do the integral. So pi integral from a to b f of x minus k squared minus, not plus, minus g of x minus k squared dx. Now the reason I don't love this formula is because if you look at this, it's like, okay, well you have f of x, but you're subtracting negative 1. That's where the plus 1 comes from. You're subtracting the k value of negative 1. If k was up here at like 1, then you're shortening your radius. So it'd be f of x minus 1. But the tricky thing here is sometimes you have negative functions, and the squaring is going to always make sure that you're positive. You just have to be very careful about making sure you're getting the correct distance that you want. So same thing works like if we were rotating around a line up here. Okay. Now this one's especially weird if you're going to think about that like minus k. So let's say this is like 4. To get this radius, the way I think about it is, well, 4 brings you all the way down to the axis. I'm taking away the f of x. So this guy is going to be pi integral a to b. It's going to be 4 minus f of x squared, right? Because that gives me this guy right here. And then the, oh, sorry, this is wrong. That's a short radius. I want the long radius first. The long radius is going to be 4 minus g of x squared. Do this correctly, it'll go a lot better. So you have 4 minus g of x squared. And then I'm going to subtract the small radius, which is 4 minus f of x squared dx. Now, once again, oh, too far. Once again, we could have done f of x minus 4. Let's think about what that would be, and g of x minus 4. So we could have done g of x minus 4 and f of x minus 4. Let's think about what that would do. So, keep jumping the gun on that one. So, if we think about g of x minus 4, if you do g of x minus 4, what that's going to do is actually going to give you a negative value. Right? G of x minus 4 will give you this distance, but it'll be negative. Since you're squaring, it doesn't matter, right? So this f of x minus k and g of x minus k, useful perhaps, but I think it's much better if you just look at the picture, try to figure out how am I getting the correct length here, and how am I making sure that I'm getting the right shape of the washer. Okay. This takes practice. You have to do a lot of these problems before the AP test to make sure that you understand how these work. You're going to have 2 of them today on the sheet that you're going to get. Cool. So now, what about shells? Everyone's like, well, don't shells play a role here somewhere? Shells are actually not required by AP. So I think that's important to say. So if you want to just ignore shells, that's just fine. If you really like shells, like if you remember back, like, oh, I thought shells weren't that bad. Okay. The way that you use shells is if you have a function, maybe something like this, and you want to rotate it around the y-axis. But you know y is a function of x. The tricky thing is if you want to rotate around the y, to make a washer, you would have to have a horizontal stick like this. And then it's going to come over here, it's going to make a washer. But if you're like, well, I don't want to make washers, I want to do it with the x-coordinates still, you can. So the way that you do that is you make your vertical stick instead. And you say, okay, it's going to come over to this side, and it's going to create this kind of shell-shaped thing, and I can still integrate from A to B. Okay, so A to B does not have, you don't have to worry about like subtracting the distance away from your axis of revolution anymore. All you have to think about is where do I start and where do I stop. And the shell formula, if you want to remember it, is 2 pi integral A to B times, I gotta think about this, 2 pi RH. So it's going to be your radius, which is usually your x value, so just from here to here, that might require changing the value if your axis is moved somewhere. So usually it's x f of x, something like that, dx, because you want 2 pi rh. If you were to unwrap this shell, h here, 2 pi r down on the bottom, because that's going to create the circumference of the shell. So you're really integrating here 2 pi r times the height, which is the function. So that's shells, if you want to remember it. Like I said, AP will only require you to know washers. So if you don't know the shell, it's not a huge deal. All right, last thing I've got here is similar cross-sections. Just remember, similar cross-sections, I think this is really the easiest of the bunch, but after you learn all this stuff with the revolutions, it kind of gets muddled. So I just want to go over a couple things here. One is that if you're looking at a similar cross-section, always draw a picture, because it's going to be very helpful in making sure that you don't make a silly mistake. So like this function looks like it's root x, y equals root x. But what is the base of the square? Is the base of the square just root x? Root x is from here to here, but the base of the square is twice that length. So if you're thinking about the area of a square, just make sure you know the bottom is 2 root x. This is 2 root x. So then the area of that square would be 4x. 2 root x times 2 root x is 4x. So you would integrate from, looks like 0 to 4, 4x dx, because that is the area at any one of those x points. Every single one of those x points, the area is going to be 4x, so you're going to integrate that from 0 to 4. Notice there is no pi out front. People always put pi out front of similar cross-section problems, but unless you're dealing with circles and you actually need the area to be something with a pi, then it's not going to be there. This guy's a little bit easier, it looks like. If we were to think about this function, that's kind of like curving back here, that is the entire base of the square now. So for this one, let's say that function looks kind of like a semicircle, I don't know, but let's say this is like, I don't know, 2 and this is 5, something like that. Okay, so this guy you would integrate from 2 to 5, and then this function, let's call it the bounding function, let's call it f of x. So the base of the square this time is exactly f of x. So it's going to be integral from 2 to 5, f of x squared dx. Because you're integrating from 2 to 5, and the height of the function is actually the base of the square. This one, you kind of have to go the opposite that we did with this guy over here. We have to think, okay, we have a semicircle. So first of all, let's see if we can find an equation of this line. The slope is -1, and we have we could use either one. Y-intercept is 6, so you could go mx plus b, or you could do point slope form with either of these. I'm going to do point slope with this guy. So we got y minus 6 is equal to -1 times x minus 0, which is just x, or y equals -x plus 6. So for this guy, the semicircle has a diameter that goes from the axis to the curve. I don't want the diameter to find the area, though. I only need the radius. So the radius at any point is going to be half of the function. That's -x plus 6. And the area of a semicircle is, of course, 1/2 pi r squared. So that's going to be 1/2 pi times 1/2 -x plus 6 squared. And we're going to integrate that from, looks like 0 to 6. So this time, notice there is a pi, but it's because we're finding the area of a semicircle. So that's really all there is to finding areas and volumes. I know it was pretty quick, but do give the blue sheet a shot, and then try the other review packets that we've been given. You also are going to get a free response packet today. I would suggest timing yourself on that. The suggestions for that are on the board. Take a look, and if you have any questions, let me know. Things that are coming up that are due: pink packet, multiple choices due Thursday, and the white packet will be due on Friday. Any questions, feel free to send me a text. Love you guys. That's why I'm here. Have an excellent day.